Okay, so welcome to class. Announcements. Not really any announcements. Josh Seidel is due tonight. Should be fairly simple. I've already got quite a few submissions for it. It even tells me I have to grade 3 of these things. And today I'm going to talk about the MPI Pi project, and then some more stuff that we're going to need to know for MPI Jacobi project. So, let's see here. Today, this is what we're going to be talking about. MPI and domain decomposition. So, the MPI Pi project. Alright, so the MPI Pi project, what we have to do is we have to integrate from 0 to 1 this fancy function. It's like 4 over 1 plus x squared. Is that right?
Yes.
And that should equal pi. But since we're doing this integration numerically, using the trapezoidal rule, it actually ends up looking like 0 n of half of that, and that's going to approximate pi. Right? So the way we're going to parallelize this using MPI is what we call domain decomposition. So in this case, our domain is from 0 to 1. And so here's 0, here's 1. And basically what we're going to do is say that we're going to take this domain and we're going to, if we have n processors, or we'll say 3 processors, we're going to cut the domain, we're going to decompose the domain into 3 separate chunks that are of equal size. And then we're going to say, all right, you perform the integration on this chunk, so that goes to processor 0, you integrate it on this chunk, and you integrate it on this chunk here. And then at the end, you add everybody's results up to get your final answer. And we can do that because summations are nice.
Don't you need to be dividing by like an area? Or
Yeah, there should be a dx on here, you're right. Should be a delta x.
or yeah, multiply.
Yeah, there should be a delta x there. However, this is what I'm going to call the continuous domain. We're not actually dealing with a continuous domain. We're dealing with a discrete domain. Like this. Okay, so this is x equals 0 and this is x equals 1. Okay, so instead of dividing it up equally, that would be like each section here, this would be 1/3, right? Instead, we have 0 to n pieces that we need to divide up. And so we can say that, all right, so each processor is going to get so we're going to say each processor is going to get 1/3. So we take n and we divide that by 3, and so each processor is going to get this many. I know those aren't equal, but you get the idea. So now we have to ask the question, what do we do if n does not divide by 3? Nicely.
Get as close as you can.
Get as close as you can, exactly. And the reason being is what we're going to talk about is what we call load balancing. So if processor 0 is doing this many, and actually if processor 1 is doing this many, and processor 2 is doing this many, 2 is doing a lot less work, since I drew this badly. 2 is doing a lot less work than 0 and 1. And so what we get is, if we look at, say the time it takes here, and this is processor 0, 1, and 2. Processor 2 gets done, but 0 and 1 take this much time. And so what we have, this is a bunch of wasted space, a bunch of wasted resources. This is termed load balancing. And so you want to minimize your load imbalance as much as possible in order to fully utilize all of the computational resources at your disposal. And the book goes into a lot of technical descriptions on how all this stuff can work, and especially when you're dealing with communication. I'm not really going to worry about it too much, but it is important to know that basically you want everyone to do the same amount of work and not have to wait for anybody else. So let's see here. Let's take a situation where n is not divisible by 3. So what we're dividing up here is the actual chunks. So this would be chunk 0, 1, 2, 3, 5, 6, 7, 8, 9, 10. Okay. Actually, let's do one more. We'll do 11. So if we take 11, divide that by 3, what are we going to get?
3 and some.
3 and some. Okay, so it would be 3. Which means that, whoops, I need to write 10. Hey, go back. Yeah, see if I can make my eraser work. There were 11 there. I got confused. Go ahead. I'm going to move you over here so I can see what I'm poking. All right, so processor 0, he takes these first 3. Okay, processor 1 takes the next 3, and processor 2 takes the next 3, like that. Okay, so what are we going to do about these last 2?
Put on another one. Oh, you're only using 3?
We're only using 3.
Oh.
So what are we going to do with those last 2?
Split them up between.
Split them up.
So put 1 on 0 and.
So we can say, okay, you need to go over here, and then you go over here. And that's better. Now these two have 4.
It'd be better if it was continuous, like.
Okay. So that's the other option we could do. Is it would be better if we could split it up in a continuous fashion. And so we say, okay, so you need to take 4, you need to take 4, and then you take the last 3. Now our load balancing is much better. However, that's actually pretty difficult to actually code. And so this isn't optimal, but it's what I did when I did this project. Divide it up as best you can in threes, like so. And then the last process, well, he just gets everything else. Okay, and that's actually really easy to code.
I thought you only had 3 to work with, though. Is that what you're saying?
Yeah, so I'm tacking on these last two. Process
okay.
of 2.
I see.
Like that.
Okay.
Because he was getting the last section anyway.
Yeah.
So,
Well, that's only really an issue. I mean, that's only really that big of an issue if your number of processors compared to your things that you're splitting it up amongst are really close to the same magnitude, right? Because if you have if it's 10,000 as opposed to 10, then
Yeah.
2 more on one processor isn't going to be
isn't going to be that.
going to be a big deal.
Yeah, exactly. And it depends on how much work each one of these pieces takes. You know, if it's really if each piece takes an hour,
Then yeah, it's going to be huge.
then yeah, it's going to be a huge problem. And so you need to do it as well as you possibly can. Whereas for our Pi program, it's basically instantaneous. So I think I ran it up to 1 million, and it still was done in less than a second. So anyway, that's how we do domain decomposition in 1D. Now I want to talk about how do we actually go about implementing this in MPI. So here's our chunks here. We have n chunks, and we have p processors. So we're going to divide our n, so we're going to say we're going to call this n. Within n, we divide it by p. All right, so each processor is going to get dn number of chunks, number of work packets. And so that's going to take this array here and split it up like that. All right? And then, so we can actually index these. This is 0, this is 1, this is 2, this is 3. Right? And so we can say, all right, first off, we need to know what is our rank. So if I am rank 1, well then I need to take this section. If I'm rank 2, I need to take this section. And so the way we actually split this up is we're going to say that we're going to say n start is equal to dn times rank. Well, and end is equal to dn times rank plus 1. Right? And so that says, okay, if I'm rank 1, I'm going to start at dn, which in this case is 2, so 0, 1, 2. Right? And then I'm going to end at dn times 2, which is going to be 4. And if you write your loop correctly, you get I equals n start, I less than n end, I plus plus, just like that. So any questions on that? Make sense? Okay. So that basically says I'm going to do my chunk from here to here. So that's very straightforward. Okay, so I think that's about all you need to know for the MPI project, which is due Saturday. And then, so now we're going to talk about how do we do domain decomposition in 2 dimensions. So this is what we're going to need to know for a Jacobi solver. So this is our domain. It runs from 0 to 1, 0 to 1. Or in the discrete version, come on. The discrete version is going to run from 0 to n. So, and for just purposes of exposition, we're going to say we have 9 processors, right? So how do we divide up our domain amongst our 9 processors?
3 by 3.
3 by 3, okay?
Or 1 by 9, I guess.
We could do a 3 by 3, or we could do a 1 by 9. Okay. So here's the question, is one better than the other?
Depends on how your memory's split up.
What do you mean it depends on the memory?
Well,
They're
I
all
mean, I'm sure one of
separate.
Oh, yeah.
Yeah, this is
okay.
not shared memory.
Right.
So the one on the left has different amounts of communication that'll be required for each processor.
Okay.
Well, the one on the left, you have to worry more. You have to communicate 2 ways rather than just one.
Okay, so it might be harder to code.
Yeah.
Okay.
But maybe not at the same time, because, well, there's MPI has stuff to make that really easy.
Okay.
I'd say in this case, the one on the left has less information that's getting communicated.
Okay.
The boundaries between different regions are shorter.
Yes.
So
Yeah, and that's the big thing I want to talk about is whenever we do a communication in MPI, we are going, that is not useful work, not what we consider work. Our work in this case is computing the solution, and communication is not computing the solution. And so that's going to add to our serial fraction. So the other thing I need to talk about is, let me draw this here. Let's say here's our grid, okay, and let's say, okay, let's say our domain is split down the middle. Our domain is split right down the middle like this. Right? So our Jacobi stencil, for solving, say, this node, we need information from these nodes. But the node on the right here is owned by a completely different process. We don't know what the value is there because we don't have it. So what we need to do is this process, we call it P right, and this is P wrong. So P right needs to send this value to the other processor. So that way he can actually use it. And this is the communication that's going to be necessary when we do the solver. Not only that, but in order for P right to solve this node, he needs to know that one. So P wrong needs to send his values to P right in order for them to work together on this problem. And so, like Zach said, the amount of communication, if we can minimize the amount of communication, we can make our program go faster. And this one here, this division minimizes the amount of communication. So let's just look at processor 4 here. In our situation, the communication is governed by the surface area, if you will. So the surface area of processor 4's piece of the domain is L divided by 3 times 4, okay? And that's his surface area. And then the volume is the actual useful computation work is going to be L squared over 9, right? And so then you can generate a ratio, a communication to computation ratio by dividing the two, and I did this earlier.
So that one's actually worse,
Yeah.
but the rest of them would be either better or, well, or the same.
Well, yeah, so this is the worst case. Number
Yeah.
4 has the worst possible case, because these other guys, they only have 2 boundaries or 3 boundaries. But we want to look at the worst case, because he's going to be the guy holding everyone up. Okay. So if we do that, then if we do the surface area divided by the volume, we get a communication to computation ratio of 12 over L. And then for this situation, our worst case is going to be, well, most of them, except for the guys on the ends, is going to be 2 times L. And I never did draw L in here, but L is that. While the actual computation volume is,
Should be the same, right?
yeah, it's L times L over 9. So you see that the actual computation done is the same, but the communication is going to be different. And if we do our ratio, it ends up being 18 over L. So you see that there is more, this ratio is bigger than this one. It's slightly bigger, it's not too bad, until as L gets bigger, that ratio keeps dropping, but this one's gonna drop faster. It's just worse. Okay.
Well, the more processors you have, the bigger an issue that's going to be, right?
Yeah, exactly. We could have done it using N processors. I guess you can do that and see what conclusions you can draw from that. Right. So, yes. Okay. Nope. Can't erase something on the side. That is lame. Just gonna say that. Give me a new slide. Alright. Okay. So the other thing, so now the question is, how do we actually implement this? Okay. Especially if we want to be able to implement this using any number of processors. Okay, from 1 to infinity. And So if we start our program, we have this is our default communicator, MPI com world. Okay, and if that is our default communicator, it gives us basically a list of processors. Now the thing is, these processors have no structure, they have no relation to each other. What would be really nice is if we could take all these processors and structure them in the same fashion as we are going to decompose our domain. Like this. And so now we can say, well, processor 0, he's got a name which is to the left or the right. And so now, if the processor is number 4, we can say, okay, my left boundary here, I need to send to processor 3. And so then we can ask, okay, who's to my left? I mean, it doesn't have to be 3, it could be anybody. And so we say, who's to my left? Oh, it's number 3. Okay, then I'm going to send my ghost nodes, as they're called, or the information that he needs to know, I'm going to send it to him. Who's to my right? It's number 5, I'm going to send that to him. Okay. And so this is what we call a Cartesian topology. Another interesting thing is that sometimes the hardware itself is hardwired in a certain topology, like this. And so if the MPI implementation is smart enough, and you say, I want a Cartesian topology, it will literally map them to physical hardware, and so it speeds things up that way. Okay. Because then processor 0, he would have a direct connection to number 3 and a direct connection to number 1, rather than having to go through a network interface. I don't think we have access to anything like that. Those are kind of specialized, but they do exist. And so the way we're actually going to do this is so common, I should say, especially using MPI, that MPI provides us with some convenience functions to actually implement this. So the first function is MPI dims create. And you give it the number of nodes or the number of processors. And then you give it the number of dimensions. So in our case, this is always going to be 2, but it could be 3, it could be 4, it could be any number. And then you're going to give it an array.
You can do 4.
Yeah. Oh. You can do any dimension you want. It'll take it.
Sounds awful.
You can't see in 4 dimensions, but yeah. The computer doesn't care. It just runs the algorithm. And then you pass in an array. Okay, so what it does is it's going to take these 12 nodes, and it's going to factor them as equally as it can into 2 dimensions. So in this case, it probably spit out something like 6 and 2. So dimension 0 would have 6 processors, like that, and 2 processors in the other direction. I think that's actually 7. You get the idea. So it tries to make them as squarular as possible because of the communication. Yeah, that's what they're trying to do, is minimize communication. Important things to note is that the elements in dims cannot be negative, and they must at least be initialized to 0. Okay? If you have a number stored in dims already, then it will not change that number. So if you have, what's a number that can be factored multiple ways? 25. Okay? If you say you have 25 processors, probably what it's going to spit out is a 5 by 5, like that. However, if you have 25 processors and you feed it 25 and 0, if your DIMS array looks like this before you call the function, then what it will spit out is 25 and 1. Okay. So anyway, that's completely local. It doesn't actually do anything MPI-ish or parallel-ish. The real parallel work comes in here, this MPI cart create function. So what it does is it actually generates a brand new communicator. So it takes an old communicator, number of dimensions, which again is going to be 2, the array that we just got from this function, we can feed it back into here. And then this one is really important, periods. So our example here, we have what are known as non-periodic boundary conditions, where everything stops. There is a physical wall on all 4 sides here. However, it is possible to do periodic boundary conditions like the game Asteroids. You know the game Asteroids, or if you fly off this side, you come out down here. Those are called periodic boundary conditions because you come out, you leave one end, but you come back in at the other end. Okay, and so if you have periodic boundary conditions, then the left neighbor of processor 6 here is number 8, and the right neighbor of processor 8 is processor 6. Okay, so what this does, this periods array is a true-false array. It's either 0 or 1. And if you have 2 dimensions, you're going to have an array of size 2. And it says that this direction is periodic or it is not periodic. So it can do that. Then we have the reorder flag. And reorder, it's either true or false. And if it's true, then you're telling MPI it is okay for you to change the actual rank number for this particular communicator. And so basically, if this is the way it started, all right, if the reorder flag is true, then they could be numbered 4, 6, 7, 9, 1. 9 would probably be it, probably 8. 0. It could change the actual rank numbering. And so in the blue world, or the MPI COM world, they have the blue numbers as their rank. But in the Cartesian world, they have the red numbers as their rank. However, if you set that to false, it won't change them. So then, in the end, what you get out is a communicator. And this communicator can be used anywhere you would normally use MPI COM world. Okay? So that one's pretty handy. So now we need to know, okay, so we've set up this communicator. MPI has gone and shoved everybody into a nice square for us. Now we need to know, who is my neighbor? Who am I sending to? What's my rank? What's my Cartesian index in the IJ coordinate system? And so there is the MPI cart coords function. Again, you send it now your new Cartesian communicator. You tell it this is my rank. There are 2 dimensions, and I need to know what is my coordinates. what is my ij coordinates? And those get put into this array here. And then there's the MPI cart rank, which does the exact opposite. You give it ij coordinates and it returns rank. So you could use these two functions to determine who your neighbors are. You say, okay, my rank is 1, and then you use this function to say, okay, my ij index is 0 and 2, so who's to my left? Well, zeros, and if I know it's not periodic, nothing. And then who's to my right? Well, I add 1 to I, and I send it to this function here, and it tells me the rank at that Cartesian location. However, that's a pain in the butt. So they gave us a function that does all of that for us. The MPI cart shift function. We give it our new Cartesian communicator. We tell it a direction. So direction being 0 or 1. If we're in three dimensions, we'd have 3. 2, I should say. Displacement is how many steps we want to move in that direction. Generally, that's just going to be 1. And I would tell it, I want to know who's to the left and right of me, and so it's set the direction equal to 0. Since we're calling this direction 0 and this direction 1, and then the displacement would be equal to 1, and that would tell me, okay, 1 over. And then you give it 2 pointers, the rank source and the rank destination. And the reason being is it's actually going to tell you who's to the left and the right of you in the same function call. So if you say direction 0, displacement 1, okay, that's moving in this direction, that is going to be your destination, meaning I am sending values in that direction. And then it's also going to tell us our source. Who are we receiving values from? All right, and so that is why there's 2 of these. One tells you basically who's to the left, and the other's telling you who's to the right. If there is no neighbor, such as at a boundary, so if we look, if number 5 were to call this, there's nobody to the right of him, except there's no periodic boundary conditions. So who am I going to be talking to? And the answer is
Nobody.
MPI proc null. You can actually use this in your send and receives. You can send something to MPI proc null. You can receive something from MPI proc null. And all it does is nothing. Okay, but that is valid. And okay, so that is my lecture on domain decomposition. Hopefully that should get you on the right track for the MPI Computing Pi program, and then get you set up for the Jacobi, which we'll start on next week. I won't be posting that this week, so. And I will be uploading these slides here in just a second. So, any questions? Okay.